In this video, we're going to start off reviewing a concept that you learned in 10th grade on chemical and physical changes, and we're also going to be discussing a couple of different ways in which you can represent changes. You are going to need your notebook and something to write with, and once you have those ready, let's go. Okay, so chemical and physical changes. Again, this is a review of what you did in 10th grade. We're going to get a little bit better of a definition than you got in 10th grade because at this point in time, you've learned quite a bit more about the subject. So, a chemical change is a change involved whenever you break a chemical bond. So that means you have to break an ionic bond, like for sodium chloride, you break the bond between sodium and chlorine. You have to break a covalent bond in a molecular substance, right? So for example, if I have water, I have to break the bond between oxygen and hydrogen. Or if we have a metallic substance, you have to break the metallic bond between those individual atoms. So if you break a bond, it's a chemical change. A physical change doesn't involve breaking a bond, it involves breaking a force, right? So breaking or forming intermolecular forces or attractions. So this is what you learned as dispersion, dipole-dipole, hydrogen bonding in sophomore year. Some of you may have also covered ion dipole force, which is going to be pretty relevant once we get into some stuff later on. All right, so chemical is breaking bonds, physical is breaking attractions. Now, what do you do if you have something that doesn't neatly fit into this category? Right? So for example, let's say I wanted to dissolve sodium chloride in water. Well, dissolving sodium chloride in water involves both breaking and forming chemical bonds, right? You're breaking the ionic bond between sodium and chloride. But it also involves forming intermolecular forces. You're forming an ion dipole force between the sodium ion in water and another ion dipole force between the chloride ion in water. So which is it? Is it chemical? Is it physical? Is it both? It's not always that easy to tell. A good way to kind of work your way through it is if the change could be reversible. So if we dissolve sodium chloride in water, what would happen if we just evaporated out all the water? What would it look like? Well, if we evaporated all the water out from our sodium chloride solution, the sodium and chloride ions would go back and reform their ionic bond, so it turned back into a solid, right? So the chemical change is reversible because we can reform the bond. So I would say for dissolving is best described as a physical process because of how easy it is to undo. So that was one of the rules of thumb that you learned in 10th grade, which was if it's easy to undo, it's probably a physical change. If it's not easy to undo, it's probably a chemical change. All right, so that's chemical versus physical. Now we'll just go into a couple of easy ways to represent these. You've seen one of them before. You probably haven't seen the other one that much, right? So here we have a chemical change. This is the reaction of water to form hydrogen and oxygen gas. This is a decomposition reaction. So there are two ways that this has represented that chemical change. The first way is with what's called a particle or a particulate diagram, right? So we have our water molecules up here, right? Let me just get my pen set up, right? So we have our water molecules, we react them. Now there's something missing from this equation, right? In order to get this reaction to happen, we have to input energy, and the way we do this for this particular reaction is we add electricity to it, and we form hydrogen gas, and we form oxygen gas. Now, when you do a particulate diagram, make sure it obeys conservation of matter as much as the question asks you to, right? So if the question was, draw a particle diagram for the balanced decomposition of water, I would have 2 water molecules, 2 hydrogen molecules, and an oxygen molecule. Now, sometimes they'll ask you to draw a specific number of particles. If they ask you to draw a specific number of particles, then do what the question asks you. One other thing to keep in mind is keep in mind the directions in which things go, right? So if, for example, I wanted to try to form an ion dipole force between sodium and water, sodium is a positive charge. That means that I should be pointing the sodium towards the negative end of the water molecule, right? The negative end would be the oxygen end. If I drew the sodium on the hydrogen side of the molecule, I wouldn't get points for that. So please make sure that you're following that as well. The other way that we represent it, which you've seen a million times by now, is just a chemical equation, right? Now, whenever possible, chemical equations should include states of matter. So this right here, we're going to have water. Water is a liquid. Hydrogen is a gas. Oxygen is a gas. And again, it's balanced for conservation of matter. Now, one thing you can do if you want to balance this, you are allowed to do this year, is diatomic elements can be balanced with fractions. The reason why we do this is so that we only have one molecule of the reaction, right? So an alternate way that I can write this is I can say H2O liquid will form H2 gas plus 1/2 O2 gas. Either method is acceptable. We use this method down here a lot, especially for thermodynamics. The reason why is that it's always easier to multiply by 1 a lot of times than it is to do 2's. So it just makes our process a little bit quicker. All right, so those are chemical and physical changes, and representing chemical changes as either reactions or particle diagrams.